let's start. I will, Francesco is not available, so I will take his role right now. It's our pleasure to have Rui Ni visiting Lille and giving the seminar for today. So Rui is an expert in many different turbulent flows and currently an associate professor in Johns Hopkins University. Prior to this, he did his PhD in the Chinese University of Hong Kong, and then postdoctoral studies at Yale and the Wesleyan University. And before moving to Johns Hopkins, he was also an early career professor at Penn State University. I think he will present some of his work in bubble turbulence, but he also has several other studies in different two-phase flows in his big group that we can see on his first slide. Thank you very much.
All right. Thank you so much, Martin, for having me here. I'll mute myself. And thank you for the introduction. And so today I'm going to talk a little bit about the work we did in the past 6 years. I started this project when I was a second-year assistant professor. So there's a lot of sort of a personal journey involved in this project that I want to share with everybody. It's so it's not all positive things. There's a lot of negative experience with the projects I want to share. So I'm gonna get started. I don't know if everybody study multiphase flow. So I had a very simple motivation slide to talk about the multiphase flow. So if you drink milk, I don't know if you have ever seen the raw milk. If you have seen raw milk, please raise your hand. Maybe I can get a rough idea. Before you buy it from the grocery store. So the raw milk will actually typically separate in a matter of hours. And so the separation is basically, you can see of it, there's a very clear cream line here. So above that line is basically fat. Below that line is actually the good stuff. So if you just chuck down the raw milk, you're going to actually swallow a lot of fat in the very beginning, which is not something you'd like to do. So as a result, the food industry had a process that really mixed the fat or the oil phase with the water phase, and that creates an emulsion. And but you realize that if you just do this with a spoon, you mix the two layers together, you wait for a couple hours, it separates again, right? So it's not very stable. But the one you purchase from the grocery store, it can keep in the your refrigerator for over weeks. So why is this so much longer? And the reason for that is because the oil has been broken to very, very small sizes. So this process was called the homogenization process, which is basically you push the milk through this orifice at a very high speed. So the orifice is about 100 micron in diameter, and the jet shooting out of the orifice is about 100 meters per second. So it's a turbulent jet, but at very, very small scale. So as a result, when the oil droplet is passing through this turbulent jet, it fragmented in very small sizes, up to a few hundred nanometer. And if you think about the oil droplets was 100 nanometer in size, and even the density is slightly lower than the surrounding aqueous media, it takes them forever to rise, which means it takes them forever to separate. So that's the reason it's sort of kinetically stable. So that's why you can drink very nice milk with a little bit of fat in there without worrying too much, it will get spoiled over time. So this is basically the first application where you use turbulence to fragment something to nanometer size. If you go up a few orders of magnitude, there's another application which is also very important. This is something you see on the beach, or you go for a cruise ship, you can see that outside open ocean very regularly. And that is a wave crashing into the ocean. And when the wave breaks on the surface of the ocean, engulf quite a lot of gas. And those gas actually, when they get into the water side, they start with a very big bubbles. But because of the entrained wave actually generate a lot of turbulence, the turbulence actually break those bubbles into smaller sizes. Here's a very famous Japanese painting I think many fluid dynamicists like to use for motivation, but this is a very clear demonstration of the importance of the bubbles, because all these white things, they're actually whitecaps. Whitecaps are basically water that concentrated with air bubbles. That's why it looks white. So this is a great wave of Kanagawa. The bottom here is actually a paper published by Dings and Stokes back in 2002. And this is basically the size distribution of the bubbles. The vertical axis is basically the number density, the horizontal axis is radius. And you can go all the way from sub-millimeter to a few centimeter in terms of the bubble sizes. There are two scaling laws. I'm not super convinced. Is it recorded, right? I'm very convinced there are two scaling laws. But anyway, so they have been connected to different power laws from the turbulence. I'm not gonna get into that today, but happy to talk about it. So this is basically say that over up to centimeter scale, breaking by turbulence, you can also have a lot of interesting applications. And those bubbles actually in ocean side, they actually release a lot of carbon dioxide into the water. So the ocean is the biggest carbon sink of the entire planet. So actually most of the carbon dioxide goes to the ocean. So that's why it's actually very important, because if you don't have bubbles, if you just rely on the diffusion on a flat air-water interface, it takes forever. Okay, the bubble really increases interfacial area significantly. All right, so this is an interesting problem. A lot of people have worked on these problems before. I'm just list only a very, very tiny subset of papers people have published before. But the key point is I want to study the breaking of the dispersed phase in turbulence. So that's what I'm trying to do. All right, so if you first year PhD student started this problem, how would you approach the problem? If you draw something on the whiteboard, what exactly would you draw? So when I started as a second year assistant professor, the first thing I drew on my whiteboard is a circle, because physics is to study any problem is a spherical cow problem. The bubble is a spherical one for beginning. So it's a spherical bubbles, and then it's broken by turbulence. So turbulence is basically, you can think about the eddies of different sizes. Eddies are basically the swirling flows. I don't think I need to spend too much time to explain here. And if you rank those eddies in sizes, it's a very simplified view of the turbulence cascade. You can think about there is an inertial range where the eddies from large into small scales. And then, of course, there's a Kolmogorov 1941 theory, which is I just talked to folks here to realize that there's a lot of problem with the theory. Of course, I know there's a lot of problem with the theory, but we still use a simplified classical theory 1941. So here, and in the theory is very simple. So let's say you have eddies, you find two velocity vectors across a certain scale, and the certain scale is basically R. R represents the scale you're interested in. And you can come up with a second order structure function. Has a dimension of velocity square, so like energy. So scale with energy dissipation rate R to the power 2/3. So this is something we know on the, when you average that, this is what you have. Then when you put the droplets or bubbles in the turbulence, Kolmogorov in 1949 also wrote this very nice paper about the breakage of droplets in a turbulent flow. Something to realize is when Kolmogorov did that in the very beginning, his motivation is actually to use the droplet breakup as a way to validate his theory on single phase turbulence. The droplet putting into the turbulence because it allows him to see the turbulence scales to some degree. The Hinze actually took over some of the ideas, but he make a very comprehensive framework about the breakage, because he has sections on turbulence, but he also has sections on the breakup of droplets in different type of more simplified flows. And the Hinze paper has been cited quite a lot by the chemical engineers because they have to make devices to make an emulsion. And as a result, a lot of people have been using the Kolmogorov Hinze theory since then to study this breakup problems. So in these two frameworks, there's a very crucial part, which is, so you have, let's say you have a bubble or droplets of a size D, and you have eddies, but with very different sizes. How do you study the breakup problem? So there's one very simple dimensionless number is a Weber number. So the Weber number is basically the ratio between the pressure gradient or that try to break the droplets. Basically, you can think about if a droplet put into the flow, if you push it in this direction, that droplet will be compressed in this direction, elongating in a different direction. So that's how it works. So that's a driving mechanism. At the same time, you also have surface tension. And surface tension, it's the tension that's trying to keep the droplet spherical. So the competition between them would basically determine the deformation. When the Weber number is much, much larger than 1, it's likely to deform significantly and break. When the Weber number is much, much smaller than 1, it will stay spherical. So that's a very simple idea. The issue here is, what's the scale are you going to pick? So typically for surface tension, it's the surface tension coefficient divided by the length scale. In this case, that will be bubble diameter. But the eddy energy or the pressure gradient generated by the eddy is like scaled as a rho u squared. The question is, what scale of eddy should I pick to for compressing or deforming, breaking the bubbles? So there are so many different eddies, right? We said that surrounding this droplet of bubbles, you have eddies from very, very small size to very, very large size. But which one should I pick? So this is actually a screenshot from the Hinze original paper. Kolmogorov phrased it a little bit more carefully, but Hinze said it very specifically. So what he said is those dynamic forces, basically the force that deform the droplets of bubbles, are caused by changes in velocity over distance at the most equal to the diameter of the drop. Okay, so basically the assumption is instead of worrying too much about all the sizes of eddies, I'm only going to worry about the eddies that has a size almost matching with the diameter of the droplets. Okay, so that's a very specific and also strong hypothesis in my mind. So as a result, if you do that, then you can see that the velocity square here, we can use the velocity square of this eddy that has a matching size of capital D. And then what I can do here is I can replace the u square with this second order velocity structure function, but do one thing, which is replace r, which is any eddy size, with a capital D, and the capital D being the bubble diameter. So in this case, you can see that this Weber number does not have any, does not have a lot of different length scale. It has only one length scale, which is a bubble diameter. So it simplified the problem significantly because I never need to worry about the distribution of eddies around the bubbles or droplets. I only need to worry about single size. Okay, so my first questions when I was starting as the, okay, is this correct? Can I build an experiment to test this hypothesis? Because this is supposed to be falsifiable. Otherwise, it wouldn't be a good hypothesis. So that's the first thing I did. And second thing, which is also very important, is the following questions. What about timescales? So before I talk about timescale, I need to explain why timescale matters. So as I go back to the milk situation, imagine you are a farmer. You own a cow, which is the most important property you have. And then you want to milk and then generate milk and put that into the market. So apart from the energy you had to spend on this cow, you also have to put in electricity to homogenize your milk into something the grocery store would accept. So how much electricity would you spend every day? So this is a very important question. So it's an electrical bill you have to keep. So the electric bill depends on two things. One is the power, and the power basically is the same as the energy dissipation rate of the turbulence you generated. Second is the time, because how much you're going to run, how long you're going to run this facility, determine how much electric bill you have to pay. So that's the reason time scale matters. So time scale determines the time it takes for droplets from this size to reach the size I want. Okay, you can go through multiple breakup steps, but this is the time I want to be as short as I can. So this time scale, how do I model this time scale? So historically, the way people would talk about the time scale is basically on this eddy turnover time. So eddy turnover time is basically, you can think about it, you have eddy length scale and you also have eddy velocity scale. The ratio between them give you a turnover time. Again, because you have so many different eddy sizes, there's really no set time scale here. However, if you extend the Kolmogorov Hinze hypothesis by saying that I only pick the bubble size to be the relevant time, the length scale, so I can replace the arbitrary R to a very specific D, and D being the bubble diameter, then I have an estimation of the time scale it takes for the breakup to happen. Okay. Comes to the second point, is this hypothesis that has been used so often by the chemical engineer, is that valid? All right, so my talk is going to just address these two problems. In order to do that, I had to build a system. So in the very beginning, I realized that what I need is very intense turbulence. And the reason for that is very simple. If you put air bubbles in water, you may not realize how much energy is stored in the interface. The interfacial surface tension between air and water is extremely large. Okay, so in order to break it, we need a very specific facility. I will tell you why later. So this is a vertical water tunnel. The reason I have a vertical configuration is because the following slide. But here, the vertical funnel has this test section here, and it has this interesting name, but the most important part is that it generates turbulence. The rest of it is not very important, just for a cool name. So the very important feature of this is I have a controlled mean flow. So the mean flow is actually pointing downward. The reason I have the mean flow to pointing downward is because I want to keep the bubble in the test section for a long period of time. So the bubble was injected from the bottom by a bunch of needles, and they were slowly rising to the measurement sections. And I have this mean flow that coming down. I don't know if you guys can see the video here. This is the first video we took back in 2016. And this is basically the bubble really trying to go up, but it can't because you have a mean flow coming down that matches with rising velocity. The rising velocity is about 20 centimeter per second. As a result, the mean flow is also tuned to about 20 centimeter per second. Okay. The problem is if you have a 20 centimeter per second mean flow, you cannot generate very strong turbulence. And certainly not enough to break the bubble. You can see those bubbles never break, right? They just keep going up. They're doing this spiral motion, but they never break. That means the turbulence is not intense enough. So in order to make the turbulence a little bit intense, the solution we came up with is, in the literature, there are two options. You generate turbulence, you either use a passive grid or use an active grid. But in water, using active grid is extremely tricky because you can actually have a lot of leakage through the shaft. So we decide not to use an active grid, so we decide to use a jet array. So jet array is actually, it's a idea I like to claim I came up first, and I also realized that Stanley Corson did it back in 70s. So I didn't really come up with this idea. But the idea here is instead of using active grid, the rotating fins are using jets. And the jets are randomly shooting and they merge against each other. So you can generate almost like a homogeneous isotropic turbulence. Except recently I published a paper to claim that it's not exactly homogeneous isotropic turbulence because the jet features actually stays for a long time into the test section. But that's another story for another day. So the jet array looks like this. We have this 3D printed. And the reason we have this 3D printed is because there's a lot of internal channels that have to deliver the flow in a way that I want them to be. So the feature here is you have a lot of square holes. The square holes allow the mean flow to pass. But at the same time, I have a lot of those circular nozzles. Those circular nozzles actually are jets. They're basically connected through a very weird configuration to the side holes to allow you to inject the flow, because everything is a piping and it's very easy to seal them. So if you're cutting in half, this will give you an internal view. So the mean flow will go through the square holes, and the jets will pass through those kind of side holes and will shoot coaxially with the mean flow into the test section. And the jet velocity will continue from 5 meters per second to 15 meters per second, which means we have a good way of control the energy dissipation rate. All right, so, and the bottom is a Capri islands allowed to inject the bubbles. Bubble rise to a certain location, and we have to make sure that this location is far away from the jet, so the bubble doesn't get hit by a single jet directly, but instead by the turbulence that merged from the jets. And then I have 6 cameras. So the test section here is the octagonal test section. So again, a mistake. So if I do it again, I probably won't make it so complicated. But at that time, I make an octagonal section because I want to have optical view on all sides. And then I use 6 high-speed cameras. I borrow 6 high-speed cameras from my colleagues. So here is basically the view of the experimental setup. So each high-speed camera has an LED panel on the opposing side to allow you to see the shadow of both bubbles and the particles. And the reason we have to do this configuration is because we want to make sure we can see particles all around the bubbles in order to see the eddy interaction with the bubbles. That was the original goal. So once we did that, this is one image. I have the dark, like those weird-shaped things. They are bubbles. You cannot really see particles on these images directly, but then I can separate the bubbles, I can separate the particles, and I can zoom into the particle field so you can see there's a single bubble with a bunch of particles in the surrounding areas, and you can see we put a lot of particles so in order to see the eddies around the single bubbles. We have 6 cameras, so which means we can see the flows around almost each corner of these bubbles in order to make sure we capture the intermittent events. All right, now I want to explain myself a little bit. Why do I use 6 hammers? The reason I use 6 hammers is because I have limited views. For example, I don't know if everybody here does three-dimensional measurements. Okay, I know not everybody here doing three-dimensional measurements. So imagine everyone knows how to do 3D measurements because you have two eyes, and each eye is one two-dimensional cameras. With two cameras, you can measure the three-dimensional world. So now we know how to do that. But the problem is, in order to see the same thing in 3D, you need to make sure every object can be picked by two cameras simultaneously. So if you're, for example, if you remember the image I showed you before, the bubbles actually look dark, which means block the light in front and in back of this bubble, which means along this optical path, this camera cannot see any of those particles along this path, which means all the dots in red can only be captured by less than one camera, which means they will never be able to capture them in 3D. Only those green particles, they can be seen by both cameras, which means they can be reconstructed in 3D. But then if you only rely on two cameras, you realize that you only can measure the flow in this corner and in this corner. You lose majority of flow on the other dimension, and this is three-dimensional flow, and that's a disaster. So I had to put the other two cameras on the orthogonal directions, and some of those red points will become green, which means they can be reconstructed 3D. But you realize that I still have blind spots. Those spots are very close to the bubble surface. You cannot get them. That's the reason you had to put another two in order to reduce the number of blind spots as much as you can, so you can get this three-dimensional flow more or less cover the entire bubble interface. So that's the reason. Okay. At this point, I already spent all my startups. I built a tunnel, I buy and borrow some cameras, but then I realized that still the traditional tracking system back in 2016 is not enough. I inherited the particle tracking system from Eberhard Bodenschatz group, and the concentration was not high enough because at that time we prioritized for long trajectories, not for concentration. As a result, the tracking system is not exactly what we want. So I spent another 2 years to develop the technique. So I borrowed this idea from the shake the box method, which now has been widely used in the community. It wasn't very common back in 2016, so I decided to write my own code because I thought I wrote a code before, I can write a shake the box code. Then till this day, I'm still struggling with the second version of the code. But anyway, so it works, at least for our group. So we wrote the code for parallelized shake the box code to increase the particle concentration we can track. And I put this on the GitHub, and we're going to have a second version out very soon with a GUI, so that allows everybody to use it more easily. But anyway, so this is my contribution, hopefully, to the community. Someone, please use it. So then that's give you the particle and the flow information, but at the same time, because the deformation of bubbles in turbulence is extremely complicated, it's not really it doesn't deform from a sphere to ellipsoid. It deforms in a very complicated way. So in order to make sure we get the interface, the geometry correctly, we also spend quite a bit of time to deal with the reconstruction method. So this is actually not a real data. This is synthetic data we got from our department chair, Greta Tryggvason. And the right figure here is showing the reconstructed volume versus the direct numerical simulation volume. I feel weird to say that we use DNS to validate experiments, but this is the only time I'm going to say that. So this is just to show you that they match pretty well against each other. All right, so finally, after 3 to 4 years of struggles, we finally get to this point. I was very happy because that's actually the day I moved from Penn State to Hopkins. And I didn't tell my colleague here, I haven't gotten my first data after 3 years. So that's probably the reason that I got hired. So now, so this is the data we have. So you can see that in the middle, you have a bubble is deforming and eventually will break. And simultaneously, we have particle tracks around this breaking bubbles. And you can see that we have quite a lot of a tracer particle in this domain, which is about a few centimeters. So this is the best results we can ever get. Even that, the concentration is not high enough, but we're trying to, this is probably the state of the art at that time. All right, so now we have a lot of those breaking bubbles because in the experiments, we can keep recording. We have tons of data. We have, I'm trying to get my number correctly, hundreds of thousands of deforming bubbles. The breaking events are relatively rare. It's about 100 to 1,000 cases, and we have tons of trajectories around them. So that's why we have to use our own system, because our system can be run on clusters, so you don't have to rely on desktop. So you can get a lot of data processed simultaneously. All right. Now I'm gonna switch to the physics. Okay, so the first part is very sort of simple. It's just the second order structure function. You average over many pairs of tracks, and then eventually you can get a second order structure function. It's not perfect, so you have something look like this. So we can get down to about a 6-7 Kolmogorov scale at most. And the inertial range, the scaling is not perfect because I have finite Reynolds number effect. Our Reynolds number is around, Taylor scale Reynolds number is around from 200 to about 500, depends on the jet velocity you tune. But you have a reasonable scaling loss for the inertial range. And then this is for this particular case is about 400. What's important about this setup is energy dissipation rate. For most of the facility that are being used to study the homogeneous isotropic turbulence in water, the energy dissipation rate is typically low, except for the French wash machine, the von Karman flow, that you can get decent energy dissipation rate. Otherwise, it's always too low to break the bubble. But for a French wash machine, it's actually not ideal to use for breaking bubbles because the propellers actually break the bubble more often than the HIT, or not HIT, but the turbulence in the center. So here, it's basically, this is probably order of magnitude higher than most of the setup. So that's why we can reach the regime when the Weber number driven by turbulence is stronger than the buoyancy driven breakup. So that's why we can study this particular regimes. And the bubble size is actually within the inertial range. So we know that they encounter the inertial range sort of eddies now that get too small to large scales. All right. So far, I basically spent a long time to build the measurement techniques and also make sure the system can deliver the flow we want in order to study this particular problem. So I want to talk a little bit about the data processing. So imagine you have this data in the year 4. Okay, I hired 2 PhD students in US. It's a 5 years PhD. So they spend the first year working on the courses, and then close to the graduation they have the data. So the last year was really trying to get the results. So this is the result they got. So you have a bubble trajectory. This is basically bubble trajectories. I skipped every about 50 frames so you can see their shape. And with the bubble trajectory, you can easily get the bubble velocity because, you have trajectory, you can easily take derivative to get the velocities. And then for each instant of the bubble, you can take a search volume, you can find all the tracer particle within the certain distance with the bubbles, and then you can get their trajectory, so you can get a velocity too. So eventually you get a bubble, it's a velocity, and you have a bunch of tracer particles around it. So now you know the velocity of the particle. So I use a UIP, P stands for particle, I stands for indexes, and the X now is the center. So now what can you do? So this is the first question I asked myself. The question I posed in the very beginning is, the Kolmogorov and Hinze assumption is they only care about eddies of the bubble size. They don't care about the eddies much smaller or the eddies much larger. Okay, so that's a hypothesis. So right now, the question is, I'm an experimentalist, how do I separate the eddies of different sizes? So when I deal with this problem, the simplest way I thought about it is, let's just do a Taylor expansion, right? So imagine you have a bubbles with a bunch of tracer particles in the surrounding areas. I can do a Taylor expansion. I get the first leading order, which is basically assuming there's a velocity almost constant in this area around the bubbles. And second is basically the velocity gradient, cost gradient at the bubble size. And the third term, a high order term, is basically the smaller eddies. So if you decompose that into those terms, the Kolmogorov hypothesis is basically on the second term, which is basically the velocity gradient tensor cost gradient at the bubble size. And then you can define a Weber number based on this velocity gradient tensor. You can get the strain rate tensor out of the velocity gradient tensor, and then you can get the 3 eigenvalues corresponding to 3 eigenvectors. Putting in the simple terms, imagine this is the bubble. You have a flow goes like this. Okay, it's contracting in the vertical direction, extending in the horizontal direction. And the contraction direction is basically the lambda 3. So I use the lambda 3 to multiply by d and square that as a characteristic of velocity square. So this is basically representing the pressure that is compressing the bubble. Okay, so if you put that as a pressure inside the Weber number, this is basically the Weber number you have. The Kolmogorov theory is an averaged value. So it's not the instantaneous value, but what we can do is, because we can track these bubbles and the surrounding flows, we can get an instantaneous velocity gradient. We can measure the instantaneous Weber number. And the symbols are basically the instantaneous Weber number distribution. And you can do the simple calculation. You're assuming that I know the dissipation rate distribution, then you can convert the dissipation rate distribution into a Weber number distribution. That's a solid line. And to some degree, I think these two agree reasonably well, except for the left end, where those are actually very small Weber number cases where the velocity gradient is kind of weak. I'm not entirely sure how much I can trust the left end, but overall shape reasonably good. All right, at this point, I feel like I failed my mission. Why? Because the Kolmogorov series seems to do a reasonable job. There's no surprises here. I mean, everything seems to work. But then I realized that there are two missing terms I haven't studied yet. One is the first term, which is, remember that the first term stands for the flow has almost a mean flow around these bubbles. So it's a uniform around the bubbles. And you can think about this as eddies or the flow contributed by larger eddies. So if you imagine this is a bubble and the flow next to this bubble that could be contributed by eddies like much, much bigger. And the flow contributed by eddy much, much bigger at this local point is almost like a constant uniform flow. So that's basically this first term. And because that the flow around this bubble doesn't have to match with the bubble velocity. So that you could have a velocity difference between the two phases. And that can also create a pressure that can compress the bubble. Imagine the bubble is moving this direction, flow is moving this direction. The bubble can be pancaked along that direction simply because of the velocity differences. That will give you the different Weber number, which is this Weber slip, and the distribution looks like that, which is slightly different from or very different from the turbulent contribution. I want to make a disclaimer here. So even though I keep saying Kolmogorov, but Kolmogorov actually had a very important hypothesis in his original paper. His original paper actually never talked about bubbles. His original paper talked about neutrally buoyant droplets. And the reason he made that claim is because if you have neutrally buoyant droplets, maybe the velocity difference between the two phases is negligible, so you can ignore this term. However, we know that from the past experiments that if the bubble or droplets, even if it's neutrally buoyant, density is matched, if it's a finite size, they still can have velocity differences. So this term could still be not negligible. Okay, but so far, everything can be explained to some extent. But that's actually not what I want to do in the very beginning. What I was really curious about is a sub-bubble scale eddies. The eddies are actually smaller than the bubbles. And the reason I was interested in that is because I always feel like the breakup is actually very intermittent events, okay? But if we keep emphasizing on eddy of the bubble size, we neglected the eddies are actually more intermittent, which is a smaller eddy. So why can we not consider the sub-bubble scale eddies? So that was actually the main questions. I was curious about this contribution. So when I started to think about this contribution, that's basically very close to graduation date of my students. And we were trying to scratch our head to say, how can we isolate these events? So in order to isolate these events, how do you do that? Well, to some degree, it's very simple, which is you move this two terms to the left side. So you subtract the mean, you subtract the first term, whatever left is high order terms, right? But there's an issue with that. Why? Because if you look at this picture here, you subtract the first term, you subtract the second term, what you're left with is very close to the noise, meaning the stuff you care about is very close to the measurement uncertainty. So to some degree, this experiment is doomed since the beginning. I want to measure the noise. So that's the tricky part. So I was very struggle with this because there's a lot of reasons. I was trying to get very accurate measurements, get down to the noise level and quantify the velocity Haitian because I believe that was a very important thing. It still doesn't work. So there's 27 components. You need tons of tracer in order to do that. The resolution is not enough. So we wasted a lot of time. So although I'm summarizing this with like 3 sentences, this is like years of work. This just didn't work. So one day I was went to the APS meeting. I was thinking about, okay, what I really need, I was reading a Harry Potter book to my son at that time. I say, what I really need is a magic knife, okay? So the magic knife has to be able to separate the scales and cut away the large scale and only give me the small scales. And we cannot use a fully developed turbulence because fully developed turbulence is always all scale present. and most of the energy is large scale. That's just nature of the fluid developed turbulence. So I said, maybe we can try to use a different flow, not the fully developed turbulence, but something else. So this is something I watched in I attended a talk by McKeown, it's and Rubinstein's group. So they basically, this is actually collaboration also with Twinter and Andrea Prosperity was part of that. Anyway, so it's a lot of people, sorry, not Andrea Prosperity, another friend of mine actually was involved in this. But the main idea is they want to study the cascade of turbulence by using a simple setup. The simple setup is actually trying to use the two vortex rings colliding with each other. And the vortex actually has a lot of instabilities, and they would generate a bunch of the cascade that causing the vortex to become smaller and smaller. So if I'm gonna play this video for a second, you can see that the two vortex rings collided, and they generate this smoke. But the smoke is actually just tells you that in the very beginning is one ring. If I show you the simulation, this is only half of the simulation. Okay, there's two vortex rings collide, but you only simulate half. So this is one ring. And later on, it becomes this cloud, and clearly the structure of the eddies becomes smaller. This is actually, when I look at this, I realized that what if I put bubbles in there? I put a bubble, I control the time it reached the flow. And in the very beginning, I have large bubble interact with large ring, and at a later time, I can have a bubble interacting with a smaller eddies. And this is my magic knife because you use a time to separate the eddies of different scales. This is actually conducted by Rodolfo Monico. I think he moved back to Spain after spending a few years when I met him in University of Houston. Anyway, so that's the setup. So this is basically we built a similar setup by two undergrad students in the group, and basically use the two pistons, you generate the flow, two vortex rings, they collide with each other. You use multiple high-speed cameras. They can also, the field of view is right here, because that's the location where you have bubbles colliding with the vortex rings. And this is sort of zoomed in view. You can actually, the field of view can capture both the large eddies and smaller eddies. And in the very beginning, I thought it's a very easy experiment. It turns out it's a very hard experiment. And the reason for that is because you had to synchronize everything, because the timing is extremely important. You had to make sure the vortex ring collide, and then the bubble is actually at the exact location you want them to be. So three things collide together. Okay, so that's hard. And also, by the way, I forgot to mention that in the very beginning, I was thinking about three things collide, like two rings and one bubble. They never do that because the bubble always sucked into one ring. And I realized later it doesn't really matter because all I care about is eddies. They're always stochastic anyway. But anyway, so right now it's basically I'm using the same methods. We use this OpenLPT method we use for particle tracking, and we use a visual Hall method to get the geometries. All right. So now I'm going to move on to the data of this particular setup. So first of all, I'm using color matching. So the structure here and the velocity structure function showing here are matched. So this is basically in the very beginning. I'm measuring the second order structure function here. You can see that majority of the energy is stored at large scales, okay? And it's in log scale, so the small scale is actually negligible. And then with a later, then you can start to see at a later stage, the large energy drops, and you start to develop this two-third power law, which is similar to the inertial range in the fully developed turbulence. So you know you start to generate a lot of smaller eddies. Then basically the large eddies start to cascade down to smaller eddies. So this is the flow you have. And then using the same color matching, so the magenta line is showing you the Weber number of the bubbles inside this large eddy, and the blue curve showing you the Weber number of the bubbles in those smaller eddies. There are different definitions of Weber number, so I don't want to bore you with exactly what they mean, but I just want to draw you to one feature. You can see that for both cases, the PDF, the magenta is on the right of the blue one. Okay, what I mean is the Weber number of the bubbles in the early stage is always larger than in later stage. So the bubble experienced larger Weber number early on with the intact with large eddies. It makes sense. Why? Because energy of the flow is decaying over time. Of course, you have more energy in the very beginning. And also because all the energy was concentrated at a scale close to the bubble size, the Weber number by definition will be larger. Okay, that's not surprising. So the primary case or early stage have larger Weber number. The Kolmogorov Hinze framework basically suggests that the primary breakup should be easier because the Weber number is larger, right? So remember that Weber number defines the ratio between pressure that deform the bubble to pressure that restore the shape. If this number is large, it's supposed to break. And also it suggests that the break should be violent because larger the Weber number, you should be able to fragment the droplets or bubbles immediately. So I will let you to be the judge to see if that's true. So right now I'm going to give you two videos. The left video is the early stage where the bubble is intact with one large eddy. And the second video on the right is actually smaller bubble intact with a bunch of smaller eddies. I'm gonna click once and they're gonna play at exactly same rate at exactly same time. And you can see which one actually break faster and more violently. And remember that the early time, the magenta line has a larger Weber number. So you can clearly see that the small eddies and the later time, even though the Weber number is small, actually breaks more violently and finish a lot sooner. Okay, and the primary case that takes forever. Okay, so this is a direct contradiction to what we expected. So the larger Weber number does not result in a faster breakup. It's actually resulting in slower breakup. Okay. And the smaller Weber number with a lot of smaller eddies, but they are energetic, so actually break it faster. All right, so this is very important. So now, I mean, this is a very qualitative. So now we want to be quantitative, so we need to build a model. So in order to build a model, the idea is the following. So the Kolmogorov theory has one scale, which is basically the diameter of the bubble. So in order to break this hypothesis, I need to assume there are two scales. One is a bubble scale, the other one is eddy scale. Okay. And then I need to come up with a criterion for breakup. So in what scenario the eddy will be strong enough to break the bubble? So there are two criterion here. The first one is a stress, which means this eddy has to be strong enough to go through the bubble and break the bubble, which means that the energy of that has to be larger than the local surface tension. We had to emphasize this local surface tension, so that's why I use a curvature of the eddy instead of the curvature of the bubble. So that's a first difference, is a local stress. If you plot that, this is the basic eddy velocity over the eddy size. This is basically this line. And in order for the eddy to break the bubble, you had to stay above this line to be fast enough, okay, energetic enough. But that's not the only criterion. Why? Because you also have time criteria. What does that mean? So imagine you have very strong eddy intact with bubble, but the eddy died before they finished the job. And then it will never breaks. So that's another thing. The intacting time or the eddy. So basically the time for the eddy to break the bubble has to be shorter than the lifetime of the eddy for the job to be finished. So this is basically saying exactly what I just said. And then you have this red line. And in order for the breakup to happen, you also have to stay above the red line. So as a result, two things actually have a different dependence on the eddy sizes. And eventually, if you want to have a breakup, this is a region that you will have breakup. If you're below this two line, below either line, you have no breakup. So that's basically, you have this criterion for breakup. This is a minimum eddy velocity that is required for the breakup to happen. This is basically what we have. So now we have this minimum eddy velocity. How do we know the breakup probability? Well, then you can use a classical, Kolmogorov 1962. All you need to do is say, this is energy dissipation. I know this is not a perfect model, but it's reasonable for what we want to do. This is a probability of energy dissipation rate of the eddies. And all I need to do is, if I know this distribution, I can actually calculate the probability of the eddy velocities that for the bubble to encounter. Then I can actually integrate this probability from the minimum eddy velocity to infinity. So basically, I only care about the eddy that is strong enough to break the bubble. Then I have this probability. I want to emphasize this probability stands for if you have one bubble encounter with one eddy, and what's the probability that a breakup would happen. Okay, so that's the probability means. And you can plot that as a function of the dE over d. So this is a ratio between the eddy size to the bubble size. If it's a Kolmogorov Hinze theory, this is supposed to be a delta function at 1, which means you only consider one size. But right now we consider a distribution of sizes. You can see two things. First of all, even though the eddy is smaller than the bubbles, you could have breakup. The probability is not 0. Second, the peak is actually not at 1, but at a number smaller than 1. What that means is it's not the eddy, that bubble size that contribute the most. On the contrary, it's actually a small eddy that is more likely to break the bubble. Okay, so that's something to keep in mind. So that's a very important message. Subbubble scale eddies are more important for bubble breakup. Okay. But at this point, I don't know if you realize one thing. I'm an experimentalist. I have this interesting toy model, but there's no connection between them yet. Okay. So in order to make this something I can be validated against experiments, I need to use this probability, but change it into a quantity that I can measure. So what quantity can I actually measure? If you look at this video again, so you have this bubbles that's been deformed, they tumble, but you realize that a lot of deformation doesn't result in the breakup. So there's a lot of collision with eddies, they don't result in the breakup, which means you have time between the two breakup events. So from this experiment, I can get the time scales. What are the time scales? There are two different time scales. Imagine I have one breakup and I result in two bubbles, and one of the bubbles is larger, so this bubble will undergo a lot of deformation and eventually another breakup. If I have two breakup events and the duration in between is basically my one time scale. This is 1 over the breakup frequency. So this is a very classical time scale the chemical engineer cares about because it tells you how fast it takes for the product can be made. There's a second time scale. The second time scale is the final moment of the bubble. So the bubble encounter eddy that is intense enough, but the breakup doesn't happen instantaneously. It will take some time for this breakup to completely finish. So that's another time scales. So these two time scales actually can be measured. So we measure the TC first because with the vortex ring, we know exactly when it's spherical, when it's actually become break. So we know the TC value. So TC value can actually be modeled because you know the probability of the breakup. You can actually know the time scale of the individual breakup events. You can integrate that again from the minimum eddy velocity to infinity. And then you can do some normalization with the collision frequencies. You can have an estimation of this from the model. And at the same time, this is experimental measurements. The experimental measurement is not perfect. The reason for that is because there's a very narrow range of the bubble size you can break. If it's too large, it will break before entering your field of view. If it's too small, it never breaks. Okay, so that's the reason the size range is very limited. Second, the error bar of the breakup time scale is big is because the student have to manually run this over hundreds of times. So the students say, I want to graduate. So that's where the error bar is going to be limited. But this is a model prediction because we take the ratio between these two and there's no fitting parameters here. So this is basically exactly what predicted from the model. Seems to be reasonable. But I'm not exactly happy with the experimental method, so I want to think about another quantity I can validate. Another quantity that is more relevant to chemical engineering, as I mentioned before, is this breakup frequency. So the breakup frequency is something people struggle for a long time. So this is one of the experimental work by Czech Republic group. And this is actually an experiment. They also inject bubbles, but they have a lot of jets. They didn't really try to maintain a homogeneous isotropic flow because they want to reach very high energy dissipation rate. The only way to get from very low energy dissipation rate to very high energy dissipation rate is get very close to the jet. So they actually vary the energy dissipation over almost 2 orders of magnitude. You can also see their size, which is different symbols are very limited. And this is basically measure the breakup frequency. If you use Kolmogorov, basically just use eddy turnover time, and you can see that you miss quite a bit simply because the eddy, this is not by just magnitude, this is the slope is very different from the experimental results simply because you missed a lot of small eddy contribution. But when you use our model by basically doing the same thing, you do the integration, but you're accounting for the small eddies up to the bubble size. And this is basically integrate all the sub-bubble eddy contributions, and this is the results you're going to have. Different color of line showing the different bubble sizes, so the agreement is reasonable. I want to explain just very quickly why we can have a better capture of the experimental results is the following. You can see that compared with the Kolmogorov Hinze model, our curves are a little bit steeper. So steeper means what? Steeper means when you increase the energy dissipation rate, the breakup frequency is higher than the Kolmogorov Hinze predicted. And the reason breakup frequency is high is because when you increase energy dissipation rate, you energize the smaller eddies. You make smaller eddies easier to break the bubbles. And the smaller eddies are basically faster. As a result, the frequency is higher. So that's the reason if you're accounting for their contributions, you have a better agreement with the experimental results. Anyway, so this was published in 2022. I think I'm running out of time here. So my summary is the same as my title. So the point of the work is we spent a long time to go through many different techniques, trying to work on the eddies that is similar to the bubble size and larger than the bubble size, but eventually found that actually small eddy is very important. I want to make one more point. We have not really seriously taken into account the intermittency. It's still the very simplified Kolmogorov 1962. So there's a lot of things that we haven't done very carefully yet. But I just wanted to give you guys a chronological order about a lot of the papers we published. We spent quite a lot of time on the techniques, but all these green papers are basically agreeing with a lot of the historical work, but really the one that challenged the emphasized the small eddy contributions very recent. I also summarized some of them into the annual review paper. The point of this paper is actually we only know very little about the breakup of the bubbles and droplets in turbulence. Bubbles, I think we have a little bit understanding, but droplets is really complicated. Droplets, the experimental uncertainty is like 2 orders of magnitude. It's all over the place. There's no experiment really agree with each other. So I think we need more research in that. With that, I want to thank everybody for your attention.
So thank you, Rui. It's okay. And so we'll start with questions in the room, and then we'll go to questions online and also in the chat, as you prefer. Is there any question?
Yeah.
Questions? Yeah, sure.
I thought that Hinze said that the eddy size for breakup should be at most equal to problem.
So that's the probability.
At most equal, yes, but it means that even smaller eddies, like you found, that D smaller than D can. So I was thinking your quote, he had the word at most.
Yes, yes.
So in that respect, I wouldn't necessarily disagree with Hinze.
No, I don't think it's so. If you look at exactly what he did in the derivation part, there's no inclusion of the small eddies. It's always the I think at most actually means the probability is at the size D, and that's why he did all the analysis only use the droplet size as a characteristic scale. He never used anything smaller than that.
But delta U squared average is the energy at scales R and smaller.
You mean say that again?
Delta U squared average, the second order structure function, is the energy at scales R and smaller.
No, okay, on the average, yes, I agree with you. On the average, yes, but instantaneously, no. Instantaneously, you still have to account for the small eddy contributions.
Well, there's no instantaneous structure function. Okay.
Yeah, but the instantaneous, I meant the pressure gradient at the instantaneous level that actually deform the bubbles.
Okay. I'll let other people ask questions, but perhaps I will come back later.
Okay.
Any other question in the room?
I missed the size of the bubble compared to the Kolmogorov scales.
It's order of 30 to, I'm trying to remember, 30 to 50-ish.
Okay. So is it justified this way of disentangling the different scale by making a Taylor expansion? Because the field is not smooth at that scale, so Taylor expansion.
Yeah, the Taylor expansion is just approximation. So it's you can think about this as a coarse grain at the bubble scale. So the velocity gradient coarse grain at the bubble scale is yeah. So it's definitely not smooth. It's because it's in the inertial range. It's not linear. So but you can still coarse grain at the bubble scale to get the velocity gradient and get a slip velocity. Yes. That has been. I think the tricky part is theoretically the slip velocity is basic velocity was determined at the bubble center when the bubble is not present. So it cannot be done. So it's approximation. Yeah.
As you have the trajectories of the particles close to the bubble, would it be possible to extract the size of vortices from the trajectories, from the curvature of these trajectories, for example?
We tried that.
Yeah.
And it didn't work because the curvature of the trajectory significantly biased. Let's say you have a very strong curvature. That's not because they have a very intense eddies. That's because the particle is actually moving very slowly. So it's because it's a curvature is a u squared divided by a, or the other way. But so you can see both acceleration and velocity contribute to that. You can have a very large curvature when the velocity is low, not because when the acceleration is high. I don't know if that makes sense. So when we did that, it was it's only geometric. It doesn't really tell you the dynamics of the flow.
Do you have a suggestion for a numerical simulation to check this prediction?
To check what prediction?
The fact that the vortices should be smaller than the size of the bubble to.
Yes, so there's Marcus Avila from he did a simulation in Germany on so what they found out is if there is a droplets, the local deformation is induced by eddies smaller than the droplets, but with a certain distance away, and that pressure gradient actually caused the local deformations. And and he plotted the contribution of eddy sizes for a particular deformation, and there was a peak, but that peak was actually smaller than the droplet size.
So I think Jim Brasser has raised his hand for some questions.
Yeah. May I have a question, please?
Okay, and Mikael, can we let Jim that he raised his hand first and then you?
Doesn't matter to me.
Okay, so go, Mikael. Yeah.
Excuse me, I didn't understand. May I have a question?
Yeah, please go.
Yeah, so, thank you. So first of all, thank you very much for extremely pedagogical talk, and so it was really very interesting. May you show the second or the third slide with your fundamental questions from the very beginning? Yeah, no, earlier one.
Earlier one?
With eddy turnover time. Yes, yeah, this one. So first of all, I completely agree with you that the velocity gradients is the responsible impact in the high Reynolds number turbulence. This is really the selection of small eddies. They really very efficient for the fragmentation of bubbles, of droplets, and so on. What I wanted to comment here, in fact, the main hypothesis of the Kolmogorov theory is not this eddy turnover time. Kolmogorov assumed that if there is no influence of the viscosity, then the time scale of the droplets or bubbles breakup is the Taylor time scale. You know, the rho dp cube over surface tension and power 1/3. And then if you will write density times epsilon times Taylor time scale equal to the Laplace pressure, then you will have the Kolmogorov Hinze times size scale. That means that your bubble in Kolmogorov theory reacts to any perturbation, to any turbulent fluctuation. But in reality, bubble select fluctuations because of its inertia. And my question is, first of all, whether or not in your experiment you observed that the difference of the density is playing on the breakup frequency. And another question is, still in as a small scale, essential small scale structure in the high Reynolds turbulence is this couple of vortices and stress. And the stress is just shear or strain, shear your bubble. Vorticity is changing, is involving by the centrifugal forces, involving the geometry of the bubble. Which one is more important? Strain in the turbulence or the vorticity of small scales on the bubble fragmentation?
All right, thank you. All right, thank you for the question. All right, there are a lot of layers of this question. I tried to answer them. The first question is about the eddy turnover time. That wasn't from the Kolmogorov's work. If I said that, maybe that was a miscommunication. So the eddy turnover time was actually used by a lot of the chemical engineers much later than the Kolmogorov. This is a kind of a, I agree with you, the Kolmogorov originally didn't really say too much about the time scale except for the Taylor scale. But it was, in his papers, there was a lot of discussions about the different limits, different regimes, instead of going to very specific things for bubbles. And as I mentioned before, it wasn't exactly for bubbles. So for your second questions, I think the bubble inertia is definitely important. I didn't mean that the bubble inertia is not important. So I started my talk by emphasizing on the slip velocity, which is basically accounting for the inertia of the bubbles. So in that part, I didn't spend too much time, but it's definitely crucial for deformation because most of the time the deformation is driven by the density mismatch. But what's important to emphasize is the difference between deformation and breakup. The deformation is when the bubble being perturbed by either its inertia or by surrounding turbulence. So, but what really finished the breakup, in my opinion, is the small eddies. Small eddies by themselves are not energetic enough to complete the breakup, but with a little bit help with the inertia, so the bubble is already perturbed out of the, it's already not a very stable state, then the small eddy can come in and finish the job. So that's answering the second question. We didn't really try different buoyancy because in order to change buoyancy, I have to change the density of the inner fluids. There are people who have done this work by using different gas, including helium to SF6. Some of them claim they have seen differences in the results, but I don't think that's due to the buoyancy, because what they claim is that when the bubble near the pinch off, when they have a neck, and because the bubble has two sides, one side is smaller than the other, so when you have a neck, your gas is rushing from one side to the other, then you reduce the pressure there and cause the breakup to happen earlier. But that's not due to the inertia, that's just due to the density effect.
Mm-hmm.
I think the third question is related to the strain or vorticity.
Yes.
I didn't really spend time to emphasize the difference. I don't really know which one is more important because to me, the direct thing that caused the deformation breakup is pressure. It's a pressure gradient, not just the pressure, but it's a pressure gradient across the interface. Both multiplicity and strain could potentially contribute and caused by the pressure changes. So it's a very, I don't want to say one or the other, but I just want to mention that in the vortex ring case, because you have this large scale rings that has a lot of vorticity, so they actually, because when you have a rotating flow, the center has lower pressure, it will suck the bubble in, and they will cause deformation for sure. But for homogeneous isotropic turbulence, it's much more complicated.
Okay, thank you. It would be interesting still the effect of intermittency to see how bubbles still react on the events of the high vorticity or high strain structures, and what is the, in fact, the breakup, the cascade breakup or just explosion, and so this would be really interesting. But anyway, thank you very, very much. It's really a pleasure to hear you.
All right, thank you.
So there's one question in the chat by Rasha Lakareshu. Actually, two questions. The first one is, can you comment on Weber around 1 on your slide 17? And why it has the highest PDF value? Is that means that scales near to the bubble size you can capture to great level? Yeah, for this.
Yeah, okay. Page. Oh, yeah, okay.
Two questions, yeah.
Yeah, so regarding the first question, why the web number close to 1 has the highest PDF, it's not a coincidence. It's in my opinion, if you study breakup, your PDF should always be around 1, because if your PDF is larger than 1, most bubble will break up before they enter your test section. So for what we have here is we have a field of view, and the bubble will rise from below. And if they have a larger web number, they would not be able to survive before entering. So the only ones that can break in the center have web number close to 1. So that's by definition the most probable case. I think the second question is any reason for eddy interaction timescale taken as a small, were there any fast moving capillary waves and associated further tiny vortices which break bubbles instead of direct Kolmogorov size eddies? We have, let me see, 26. So yes, we have seen capillary waves. They created some instabilities, but on the because our web number is close to 1, so they don't really contribute that much. For much larger web number, I would imagine that they will be energetic enough to contribute to the breakup. But for the smaller web number, the breakup is mostly driven by the intermittent eddies instead of by the capillary waves.
Is there, well, we're running out of time, but is there any other question in virtually? Rasha says thank you, and Chip says that he had to leave. He says hi. And if there's no more questions on the Zoom, is there one last question from the audience? So I maybe have just a very tiny question. Can you control the intensity of turbulence on your vortices, in your colliding vortices experiment?
Yes, but not to a great degree. So it's the piston velocity can be changed.
Okay.
But we never retried that because it's another dimension to explore. Yeah.
Oh, just
it's possible.
So thank you everyone for connecting, and thank you, Rui, again for your talk.